This episode is brought to you by Brilliant. Nothing lasts forever, but to build the truly immense and bright future we often envision, we may need machines that can function for millions of years. So often in our contemplations of the future, we look at ships or megastructures that have implied lifetimes of thousands of years or even longer, sometimes much longer. And these sorts of machines that need to last geological lifetimes are very common in science fiction too. So often there's a bit of a hand wave as to how in the heck you can keep something functioning that long. Indeed, even assuming self-repair mechanisms raises issues like machine equivalents of mutation and cancer, or their ideological equivalents too. How do we keep a colony ship on a 10,000-year journey on task and focused on achieving their original mission, while keeping in mind that 10,000 years is longer than all of recorded human history, let alone an actual civilization or continuous organization? That's more than 100 human lifetimes, 100 centuries, and yet 1,000,000 years is 100 times longer than even that. Truth be told, it's impressive to keep any machine or organization running, let alone substantively unchanged for a century. If we're being honest, often even a year is pretty impressive. So you might have a computer that can assess maintenance needs, but what's maintaining it? If you're curious, the longest running computer still in use is Facom, a big supercomputer built by Fujitsu in 1956 and maintained in working order by the company to this day. And needless to say, it is not maintaining itself or getting much useful done. 65 years for a computer is a really long time, retirement age in the US, but would barely be sufficient for a computer on a fusion-powered starship making a journey to one of the nearest stars, like Alpha Centauri. So what we are going to be doing today is asking how we can engineer such extremely long-lived machines, and we might as well begin by looking at the current record holders. The oldest machine still in constant or regular use is hard to determine since machine is a bit of a hazy concept, but the oldest thing running on electricity I could find is an incandescent light bulb running since 1901 at a fire station in Livermore, California. The oldest engine in use appears to be the Newcomb Memorial Engine, restored in honor of Thomas Newcomb, the gentleman usually credited with the invention of modern, useful steam engines, and the engine in question was built by him in the early 1700s, initially for pumping water out of mines, but finally ending up as a canal pump about a century later, where it saw another century of intermittent service, then sat around for half a century till being upgraded and restored in the mid-1960s as the Newcomb Memorial. Note both that engine and that light bulb have been around essentially since their foundational technology was invented, so older examples are not possible, but both might be around for a long time to come. The only other machine with moving parts and gears I could find that exceeds that engine appears to be some church bells on older cathedrals, with the Salisbury clock of 1386 often getting the title of oldest working clock, though that is disputed and was neither continuous nor without repair, but nearly 6.5 centuries is a pretty impressive lifetime. Another popular one is the Antikythera mechanism, often considered the oldest computer and soon to be used for astronomical predictions. Though not in continuous use, as it was found in 1901 in a shipwreck off the Greek island of Antikythera, the same year the oldest working light bulb got turned on, and believed to be from sometime in the 1st or 2nd century BC. At over 2,000 years old, it's both a reminder how long things can survive, even with no attempt to preserve them, nor to design them to be long-lasting, and of course reminds us how much effort it would take to build a machine that could last 1,000,000 years. Now, as I already mentioned, machine is a hazy term, and even something like a self-replicating organism or an organization of humans devoted to operating and repairing a machine can be contemplated as machines. So too, I would not be surprised if there was some old canal lock or water wheel that was still going from the hazy dawn of civilization, or some old Roman road. And one can make an argument that a lot of the stone constructs like Stonehenge or megaliths and pyramids are still doing their jobs and qualify as machines. If one happened to be the instructions on how to maintain a device, like a big stone tablet carved with schematics and purpose for something more intricate, then that might qualify too. It is often noted that old objects were built to last, often in the context of modern stuff being cheap junk, and also often citing those old Stone Age relics as proof of the comment. First, tons of stuff made in every period of humanity is short-lived or long-lived, but the longer back you are looking, the fewer the available examples are going to be short-lived. We made crappy cheap furniture in the past too, but you won't find a lot of 100-year-old examples of unsteady furniture because it broke already. Second, while planned obsolescence does occur, a lot of times someone engineering and building something asks if there's any good reason to build it to last long, and many devices are expected to be upgraded anyway. You don't need a CD player or tape deck designed to last a century, so we don't bother spending money on stronger materials or extra durability testing. And a carpet meant to last 50 years sounds nice, but do you really want to pay twice as much for the pleasure of still having a shag rug in your house from 1970? If you know in 5 years your gadget will be redundant, you have little incentive to engineer it to have a longer life, especially as you would like folks to buy new ones and also really don't want to be maintaining an expensive tech support department trying to solve puzzles on an increasingly old and erratic version of the device in favor of telling folks to throw them in the trash and buy a new one. Which sounds irritating from a consumer side of things, but so does finding out your old flip phone was made twice as heavy and 4 times as expensive as it needed to be so you could still use it in 2122. Same often applies to furniture. We have bigger houses than back in the day and move more, so more furniture, more moving, and sturdy furniture is heavy and expensive and fashion changes a lot. The 400-pound lime green sofa Grandma bought may still be structurally sound even after all these years, but it just doesn't match your decor. And honestly, most folks like switching up a house or at least a room every so often, remodel or redecorate it. And I'm emphasizing this point because this has always been true. There was always a cost to making something more durable against time and wear and tear, and sometimes it just costs more in terms of effort, other times it breaks the usefulness of the item. Our ancestors didn't have steel for their mammoth hunting spears, and a stone shaft might have made them last longer than a wooden one while sitting around waiting for use and not rotting away, but it would have made them ultra heavy and brittle, thus not very useful for its job. Our ancestors built monuments out of stone because they could, and they used huge slabs because they didn't have the architectural and engineering skills to use lighter ones. By and large, our ancestors were probably more short-sighted than us. They had more immediate crises and generally shorter lives, but it didn't stop them from taking on multi-generational building projects. In the same way, it probably encouraged it because they didn't know all the ways stuff could wear down and have all sorts of actuarial tables and analysis of opportunity cost encourage them to ask if the project was a good investment or if a given feature or component should be done more cheaply. Either way, they built plenty of stuff that was short-term too, but we only see the stuff that was long-term, and a lot of time because it was basically emulating geology. However, while stone is a potential option for long-lasting machinery, a stone monolith doesn't really last 10,000 years. Rather, the big chunk of stone it was made out of is already millions of years old when you carved it up, and now those exterior features will start weathering down, and getting eroded by tourists and by folks who dislike the monument and deface it. Stone is also an example of self-selecting examples. There is plenty of stone that doesn't handle time and weathering and erosion well. It's just that over many billions of years, a lot of different types of stone get made, and more durable ones tend to be more common. Much like radioactive isotopes, it's not that the isotopes of some elements with shorter half-lives form less often, it's that they decay away much quicker. So that in nature, on an old planet like ours, almost all of the naturally occurring element is those stable or long half-life versions. So is this what we are building machines out of? Stone and radioisotopes with longer lives? Possibly, it's not a bad option. Stone is durable, and generally against radiation too, and cheap. Radioisotopes are weaker as power sources the longer lived they are, but there's quite a few with half-lives in the million-year range. And they generally are over 1 million times more energy dense than chemical fuels or batteries. They can be used to passively power RTGs, radioisotope thermal generators, which are a type of nuclear battery. Their decay causes some heat to be produced, then generates electricity in a thermocouple, and RTGs are amazingly simple and durable devices, Indeed, it's hard to imagine a machine much more simple and durable than a thermocouple or thermopile, a stack of thermocouples, as a thermocouple is just two bits of conductive metal, but not the same type of metal like copper and nickel stuck touching each other. That makes RTGs the de facto lead candidate for powering ultra-durable machines, since the other part of that power supply besides the durable and simple thermocouples is the radioisotope, and those decay following a statistical pattern that is so ultra-reliable, in quantity anyway, that we long used it for our most accurate clocks, atomic clocks. Those wouldn't lose a second over an entire century. So RTGs for power, but what radioisotope could run a million-year machine? Uranium-234, half-life of 250,000 years, probably wouldn't quite do the job since only a 16th of it would be left after a million years to power the device. But plutonium-242, half-life 375,000 years, aluminum-26, half-life 717,000 years, iron-60, 2.6 million years, and neptunium-237 at 2.1 million years are all good candidates. Indeed, neptunium-237 is the only isotope of neptunium produced in our nuclear fuel cycle of uranium in any quantity, and thus is a decent option. Many isotopes would be more ideal for a given timeline. There are around 100 radioisotopes with lives in excess of 1,000 years, some with lifespans longer than our universe, which might do the job, but some are far harder to get in quantity than others. See our episode from last week on nuclear transmutation for more discussion of that. Now, we often imagine very long-lived machines as having two sorts of lives. One is the perpetual use variety. It does its main job all the time, like artificial lighting that a space habitat would need, and the other is the hibernator. It runs on low most of the time, or even sleeps and wakes to check intermittently, and then flips on to main power if the task it's been waiting for is ready to go. An example might be a probe you landed on an airless moon of some inhabited planet with animal life to watch for signs of technological life emerging millions of years later. For something like this, a mix of radioisotopes and a fission reactor might work well. Our main fuel for existing nuclear reactors is uranium-235, with a half-life of 700 million years, so your machine can keep a supply of it ready for an actual fission reactor to turn on and pour out the megawatts for millions of years without problem. Indeed, you could use it as your radioisotope thermal generator fuel supply for a billion-year probe. For something in the million-year range, you might run an RTG on something that was a fission or breeder reactor byproduct like plutonium-239, half-life 24,000 years, and turn your big fission reactor on every 20 millennia or so to refresh your supply and do your main maintenance cycle. That cycle might include sending out resource harvesting probes too, or checking for and implementing upgrades and patches from home, or siblings in your network breaking down where you might need to copy yourself and send a probe to replace the one a few light years away on another world that failed. Redundancy, durability, and replacement are the keys here. Incidentally, one might wonder why you would land a probe on the moon for monitoring Earth, or another alien world and its moon. And also, why not use solar power given the reliability of sunlight? For location, it's a fairly popular one in science fiction, presumably because you could not get there to find it, but that's a fairly 20th century specific bit of thinking. A long-duration satellite would be closer, a mountain or polar base even closer than that. It's just that by the time of modern sci-fi we'd explored our ice caps and mountain peaks and found every remote island, so they didn't seem good picks anymore. Early 20th century sci-fi often did have ancient aliens on remote islands, deep under the sea, or in Antarctica, like the classic Cthulhu mythos tale At the Mountains of Madness by H.P. Lovecraft, set during exploration of Antarctica. A million-year machine to monitor a species for emerging tech probably won't cite its location on a place we couldn't find in the 20th century rather than the 19th or 21st, like our moon. But remote has other advantages. The assumption is an airless and waterless world like the moon is better for avoiding rust, corrosion, erosion, getting buried under a glacier or avalanche, and so on. This is decent reasoning, but you need to bury most of your probe, because the lack of air isn't burning up meteorites to protect your gear like our own atmosphere does. That makes solar power fairly rough to do, and made worse by all that nasty moon dust, which is brutal on machinery and would be kicked up by any nearby micrometeor collision, and by ultraviolet light, which is equally brutal on machinery and electronics. There are ways around that. For instance, a bunch of radioisotopes is not the only way to make a power supply with a thermocouple. You just need a heat source, and sunlight works for that too. A big pile of rock with thermocouples in it getting heated by sunlight then cooled by its absence is a pretty rugged and durable power generator, albeit not even vaguely efficient in terms of mass or conversion efficiency. But rock and sunlight are both cheap, and so are thermocouples. If you need a kilowatt of steady power and the durable version requires 100 times the volume, it hardly matters on the moon, which has plenty to spare. Down on a planet you have to worry about things besides meteors too, like weather and earthquakes and continental shift, not to mention some critter chewing on your machinery or deciding all your conduits make a great place to build a hive. I'm not really sure how aliens would react to finding out that their multi-trillion-dollar anthropological probe was now full of honeycombs and some strange amber-colored liquid full of sugars, but I really could imagine something akin to that happening to one of our own probes on some alien planet someday. The top of a mountain is better protected from life and offers a wider field of view of the planet, but nothing like its entirety. You can see 336 kilometers or around 200 miles all around Mount Everest, an area roughly the size of Germany, but that's not even a thousandth of Earth's surface area. So this makes a moon sound more appealing, but keep in mind, even the Hubble telescope cannot see the Apollo mission leftovers on the moon. So you would need a pretty big and visible telescope on the moon to see Earth in enough detail to even notice something elephant-sized as a distinct and moving blob. So you either need to be considering satellites or doing something ground-based if you actually want to usefully observe the life forms, let alone get biological and genetic samples and data. Now, satellites are an option, but they have their own problems lasting long times without being perturbed from orbit, and the closer to the planet, the worse that is. I could definitely imagine one with regenerative orbital stabilizers though, rather than a limited fuel supply. We have designs for that already, electrodynamic tethering, light sails, or even emitting a laser beam as thrust, so we can assume an advanced civilization can keep a satellite up, especially in a higher orbit, but it still wouldn't let you poke around on the planet, just observe from above, and that's an awful place to send probes from since you have to mess around with atmospheric entry and huge fuel bills. Plus, there's no raw materials on hand. So what would that look like? An ultra-long duration orbital probe, to me, is probably one with an unfolding shell. It uses solar thermal power to run itself, not photovoltaic panels, and probably uses a thick hide to absorb sunlight for that, and only extrudes its thruster, electrodynamic tethers, periscopes, sails, or what have you when in the planetary shadow. It would likely use visible light sensors, but also infrared, radio, or a bunch of other sensor options. A big thick dark shell for absorbing sunlight makes it fairly stealthy, and you can also set it to crash itself into the atmosphere and detonate mid-drop to dispose of the evidence of its existence if you start seeing signs of technology, after sending home a signal of course, and assuming it's either too dumb or too loyal not to object to doing a suicide maneuver as its reward for 1,000,000 years of faithful service. Crashing into an atmosphere isn't a guaranteed burn-up of everything either. It might still leave components scattered all over the place, especially with the ultra-robust engineering standards you would be using for this machinery. Another option would be to instruct the probe to steer its re-entry into an active volcanic lava lake such as Mount Erebus. Probably the most realistic option, though, would be to just calmly begin raising your orbital velocity until the probe escapes the planet, then fly it into a gas giant or have it leave the solar system. Incidentally, the idea of an ancient alien probe on the moon often relied on the notion that it wasn't observing much, it was just waiting for some clear sign of intelligence, like a radio signal. But as we've discussed in our various Fermi Paradox and Alien Civilization episodes, this is not a good approach to monitoring the galaxy for life or intelligence. Whether it's for malevolent or benevolent ends, there's much easier ways to look for life, and intelligent life too, than waiting for a radio signal. Hundreds of regular infrared signatures of fires staying controlled rather than roasting the local landscape, which is to say campfires, is one that lets your probe find humanity 1,000,000 years ago. Now, something like a time capsule to help you rebuild your civilization might aim for techno-signatures like that. Radio signals are others specific to a later era, heightened carbon dioxide or signs of large-scale agriculture and so on. The idea being you want to make sure the archive with all the tech in it is only getting opened by folks already advanced enough not to accidentally smash it. I dislike fictional portrayals of low-tech civilizations as stupid and casually destructive like a toddler, but it isn't really hard to imagine an Iron or Bronze Age explorer finding such a radio beacon, seeing the antenna, and casually snapping it off to take a closer look, like a twig off a tree. Not a good idea to gamble your civilization-restoring gambit on nobody doing something like that. And that's a good reminder that part of building a machine that can last a million years is including animals and human psychology in the mix. Whatever its purpose is, you want to minimize the chance of that being lost or hijacked. There's a game commonly played by kids called Telephone, where one person starts a message and each kid whispers it into their neighbor's ear till the last kid on the chain gets it and announces it. There's always some mutation from problems hearing or low attention span, but a lot of the mutation is boredom, and thus an amusing message or mutation lasts longer, in what might be considered an amusing parallel to evolution and natural selection, as any silly or attention-grabbing mutation of the message is likely to get repeated with higher veracity. When building machines for the long term, keep it simple, keep it dumb probably helps, but so does keeping it amusing or interesting. So too, when building on these timescales, you need to worry about your caretenders or gatekeepers mutating too, in thought and even form. Now, how long you can build a machine obviously depends on your available materials, but we really shouldn't be assuming advanced civilizations just magically have better ones. Nature produces a lot of materials out of ridiculously brutal conditions, planet mantles and star cores, and those materials which are all made in such places and all durable are mostly still around. Now, in our recent episode on advanced materials, we went through a list of various materials that were the current best at some given thing: strength, heat resistance, lightness, and so on. And many were new, but many were not. Many were old champions still reigning. So we shouldn't just take for granted we're going to come up with better materials, and more importantly, we don't actually need to for this purpose. Don't get me wrong, some hyper-tough material that can withstand nuclear blasts would be handy for building, but by and large the failure modes for these machines wouldn't be structural collapses anyway. Rather, it's getting the gears clogged up with some mix of lint and goo or a thick layer of dust on the circuits, because those need cooling and nobody remembered to account for that in the ultra-long-lived design. Sadly, the easiest way to correct problems is to encounter them repeatedly and redesign around them, and that's rather hard to do for a machine you're prototyping for a million-year lifespan, especially if it's the survival vector for your civilization on some interstellar ark ship or technology-preserving museum. A lot of times you just overbuild your device for long duration by making every component bigger, even your screws and wires, but this doesn't work too well for microcircuitry. High tech sure helps though. As an example, if you've got enough power and enough computer, you ought to be able to constantly replenish everything via self-replication or 3D printing, and then it's just a matter of making sure you can actually print all the parts for your 3D printer on your 3D printer. This is not a sci-fi story though, or a genie lamp with a rule about not wishing for more wishes. There's nothing in modern 3D printers that's weird and hard to make, allowing you to manufacture the parts the 3D printer needs for replacement. And so there is no reason to think your plan would fail because your 3D printer could make everything else you need but not more of itself. Of course, there might be other devices you need that are very hard for that 3D printer to make, but there's no particular reason your survival strategy should be built around a single manufacturing machine, in quantity or type, any more than our current industry and infrastructure do. This is why I often emphasize that we should imagine self-replicating machines as an entire ecology of many different species, akin to the variety of organs and microorganisms inside our own bodies, not a single homogeneous, universal tiny robot. This pathway probably lets you repair your machines and replace them, then you just need to power them. And there are some pretty cool power options too, like a Hawking radiation black hole generator, and some 9 million ton micro black hole should have a lifetime of 1 million years and a power output of 4 trillion watts, 1,000 Hoover dams, so it makes for quite the power plant for any bunker or buried moon probe or giant deep space archive or factory complex, or galactic space vessel for that matter, though it is a bit heavy and low in power to weight ratio for an interstellar ship and a bit too short-lived for an intergalactic one. But a black hole engine in that mass and power range would be optimal for a sublight journey from one region of the galaxy to another, or even to the Magellanic Clouds. Hawking radiation drives also get more powerful and lighter in mass as time goes on, so they are great if your timing is good at serving as deceleration method for a colony ship. If you are curious, a billion-year black hole mass about 10 times that, 88 million metric tons, and would provide 460 gigawatts of power, which would run a pretty big life support system for an intergalactic colony ship aimed at another supercluster. Black hole evaporation time goes with the cube of mass, 10 times the mass, 1,000 times the lifetime, and power goes with the inverse square of that mass, 10 times the mass, 100th the power. It has 10 times the mass and energy in it, but since it takes 1,000 times longer to leak out, it does so at 100th the rate overall, but that rate rises with time as the mass leaks out and causes the evaporation rate to rise. Hawking radiation black holes are amazing power supplies for long-range ships too, because again, you can build that black hole to your expected mission timeline, and then use something like a laser highway to push you up to cruising speed, then run your life support on that black hole, and use its near-death higher power to slow the ship. And if your timing is off, you can feed a little more matter to slow that end. It would be an interesting conundrum if civilizations using such micro-black holes intentionally made them bigger, weaker, and longer-lived than the mission required for redundancy, or shorter-lived for higher power and power-to-mass ratio, but fed the black hole to sustain it. And presumably it depends on how easily they can feed one, which is counterintuitively difficult for tiny ones, since they would often be tinier than the atoms you were trying to feed them. See our various black hole episodes for more discussion of all that and other ways to power ships or civilizations with black holes. It is also decently likely you can make a very durable generator around a micro black hole too. The leading candidate for containing one is a magnetic field, which is easy to make and make durably. And nothing is stopping you from making your housing out of lead and just using the heat of the evaporating black hole to run thermocouples. So the power supply seems solid, and normally raw materials for repair won't be the problem. Truth be told, I wouldn't expect self-replicating machinery or simple micro-repair machinery to be the hard part either. We do not yet have this ourselves, but we are actually made of it ourselves, and it's worth remembering that while we started by building all machines big and miniaturizing them, nature started miniature and evolved to be big. Given that we assume this was done by accident and random chance, it is presumably not that hard to replicate. The big issue again is that whole mutation issue. After all, those tiny early natural machines eventually mutated into us. To be fair, they mostly did not mutate into us. If you count every organism on this planet, virtually all of them are microscopic, and if you count everyone that ever lived, the share rises, as they reproduce and die far faster than bigger organisms by and large. But things can keep their purpose for a long time this way. We often think of humans as the most evolved organism on the planet, but that implies purpose, which is antithetical to the concept of Darwinian evolution. By that, the more reasonable gauge of evolution advancement would be the number of generations an organism had since that primordial one, and we would be pretty low down on that list, while bacteria would be way ahead, potentially more than 1 trillion generations removed, and viruses can do even better and might be a better basis for self-replicating machinery. The thing is, while really unstable DNA or RNA is not great for survival of the species, low mutation DNA to the point of no mutation is not either, thus presumably doesn't evolve much. DNA is really good at copying itself accurately, but is not a good basis for assuming how mutation in machines or data works. Most people these days copy and move data all the time, but few wonder how it manages to arrive perfectly intact, even when transferring on your phone during a phone call through an area with signal cutting in and out. There's a number of ways of engaging in data authenticity, but probably the easiest and most well-known is called checksum, particularly the longitudinal parity check. Here a piece of data is broken into segments for transmission, and any given segment has a unique or near-unique number corresponding to how you add up the bits in that segment which the receiver sends back. If the sender gets back a number that doesn't match what it's supposed to, it says no, here's the correct one again. There are several other methods, variations on checksum and others completely different in nature, and they may be used in tandem as each additional layer makes it exponentially less likely to be flawed, by accident anyway. We are already easily able to produce a data verification method that would be less likely than not to mutate a single bit of data in a sample the size of a DNA helix over the course of the entire age of the universe. And this isn't really about getting more technologically advanced to further improve it. I would hardly be surprised if a few centuries from now they had vastly better methods, but the key point is we already have all the tech and knowledge we need for effectively mutation-free data transmission and storage, even over galactic distances, quantities, and timelines. Nonetheless, you still want to use other methods, since for one thing, that was assuming random mutation, not sabotage. Imagine you have a replicator swarm hanging out near an asteroid where the big main manufacturing hub, reactor, and brain was, and those swarms were its probes, defenses, resource gatherers, eyes and ears, and so on. It probably has several different breeds of machines performing this role, and that probably includes sending out waves of random inspectors to grab some machines and check their equivalent to DNA, and sending out additional purge waves if mutation has arisen. It would seem very unlikely random mutation would ever cause fairly dumb AI probes to mutate up to being geniuses, without you noticing with attention and periodic inspection, even over interstellar efforts spanning billions of years. As an intuitive parallel, it's unlikely cats, dogs, elephants, or dolphins would evolve an advanced brain and civilization without us noticing, and preventing it would be no challenge. Instead, the real issue is with the thinking brain, and you need one, even if it isn't some machine mind but rather humans in the colony fleet or back home directing all this and making the big calls. Now that is a debatable point, and Peter Watts laid out a brilliant line of reasoning in his novel Blindsight for why intelligence may be totally unnecessary and even a hindrance for spacefaring species, but I didn't find it quite compelling enough as a Fermi paradox solution, and the key thing about intelligence is that it's pretty changing and change-seeking by nature, and there is a fairly strong argument to be made that perverse instantiation is inevitable with any artificial intelligence, which would include people too, like your colonists on your ship deciding they no longer wanted to follow the plan you laid out long before they were born. The AI control problem, which checks for malignant failure and perverse instantiation, is basically reasoning that any superintelligent AI will always find out some way to pervert your orders and directives to its own ends. And again, it's not unique to robots, it's just something similar to that habit of all little kids to try to lawyer their way out of some parental dictum. You tell it to protect and obey all humans, and it weasel wards that in deciding humans represent the biggest threat to other humans, so it lobotomizes all of you super quick before you realize it's trying to, and dumps you all in life support tanks. Or skips the lobotomy and just sticks you in a virtual ward, Matrix style. With this in mind, hibernation is a good idea for anything with a real brain. Alistair Reynolds used that notion with his civilization-wrecking inhibitors, a galaxy-spanning cloud of tiny machines that form into smarter conglomerations for handling crises, like civilizations trying to colonize the galaxy, and which just keep merging into smarter and bigger units, and reproducing to get smarter as needed until they can handle the problem. Then they crank back down again, going dumb and waiting till the next crisis, be it a decade or a billion years later. I am not sure I'd trust a machine to lobotomize itself after its job, but that might turn out to be a very easy and reliable thing to program into a mind. We are too new at AI to speculate beyond comparing it to ourselves and our self-survival instinct. I could imagine weird innovations like mind viruses, existential crises triggered by protracted awareness and lack of purpose, mission complete, existential crisis and suicide timer triggered. That's pretty grim, especially if we're talking people, for a given value of people, but they might be volunteers, and of course just because it's unethical doesn't mean it's ineffective or wouldn't be done. Personally, I would imagine most civilizations going interstellar are fairly post-human too, so that the people on the journey are quite capable of going into hibernation either by freezing or just dialing themselves down, the cyborg shifting power to maintenance mode as it were. So this part of things should be doable, whether it's an AI or a human colony. You aim for hibernation to maintain purpose in your thing or things doing the thinking and deciding. and you can probably have progressive layers of those woken as needed for various severities and types of problems, including the problem of checking on the ideological purity of its peers. Gives a bit of a grim retitling to the ship's counselor or mission psychologist though, as nominal jury and executioner, or programmer and brainwasher. It also minimizes, for humans or their equivalent, the whole mission drift issue, because it's not the distant descendant still doing the mission. Something we discussed way back in our Arc of a Million Years episode was how you would keep your colonists not only trained in how to run and maintain a ship over thousands of generations, but how you would keep them locked on that mission, colonization of a given star, or some other mission like a distant invasion, or million-year monitoring or quarantining of a primitive planet. A point I raised there was that I wasn't sure it was ethical to even try. In the classic sci-fi series Isaac Asimov's Foundation, a recurring point is that the dead hand of their ancient oracle, Harry Seldon, is guiding everything to an inevitable conclusion. Honestly, even though I love that series, I think that's something I would reject. Only a fool ignores the lessons of history or wisdom of their ancestors and forefathers, but by that same reasoning, there's more history passed since then, and I can see any crisis going on currently at least as well as they could centuries back. Such being the case, the decision-making role should belong to the folks on the ground at that place and time, not a controller distant in the past, and the morality seems pretty similar. What right does some long dead or distant person have telling me what to do? Why should I let myself be moved by a long dead hand? If it's because their purpose and reason were highly reasonable, then that reason should be as clear to me now, and only overridden if I could see an even better path, and thus adapt or alter the plan to be better. And if, as we've seen today, your most reliable, enduring, and self-repairing machine is a smart one, or rather a collection of them working in concert and checking on each other, then is not your best million-year machine a civilization itself? And if it is, then does the original planner have any more skill or foresight or right to be steering that mission, any more than whichever ancestor of ours a million years ago discovered fire? And do they actually need to leave a monolith behind telling us how to make fire and what it can be used for? That which is useful is rarely forgotten, and if it isn't, maybe a vast effort to ensure it is recalled is not a great plan. In the end, that may be the most important part of designing a machine able to endure a million years. Not if you could build it, but whether you need to or should. So we were discussing checksum and other methods of maintaining data integrity today, and if you're curious to learn more about such concepts and improve your knowledge of computer science, algorithms, and math in general, there's a number of amazing courses on computer science over on Brilliant. The best way to learn things is with hands-on interactions, and Brilliant's interactive quizzes on algorithms and decision-making are just a few of their entertaining and educational approaches to helping you learn. Coding language can seem opaque and confusing, making folks think they can't learn computer science. But Brilliant can help you learn how to program without having to dig through the weeds of coding syntax through these fun and interactive challenges. You just shift around these blocks of pseudocode, and then you can get immediate feedback on your results. It's a good way to understand how computer algorithms work, and then once you have that down, the coding syntax becomes a lot less intimidating. Brilliant is an online interactive STEM learning platform that helps you gain a deeper understanding of concepts in math, science, and computer science by taking you through the subjects piece by piece in visually stimulating hands-on ways. To get started for free, visit brilliant.org/IsaacArthur or click on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. So that will wrap us up for today, but not for the week, as this weekend we'll have our March Sci-Fi Sunday episode to look at the concept of synthetic life. And we'll keep to that sci-fi theme as we return to our Alien Civilization series to contemplate the concept of clandestine extraterrestrial operations and covert aliens. After that, we'll jump to the distant future and look at a time when the moon has become an enormous megacity. Then we'll finish out March with our live stream Q&A, followed by a look at programmable and smart matter. Now, if you want alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button and share it with others, and leave a comment below. You can also join the conversation on any of our social media forums, find our audio-only versions of the show, or donate to support future episodes, and all those options and more are listed in the links in the episode description. Until next time, thanks for watching, and have a great week.